Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Today I will continue the discussion about the inverse Laplace transform. Last week I explained some method how to do inverse Laplace transform. We can use a Heaviside, and then we can use another method like separation. I mean that okay, maybe in another PPT, in another video in Wednesday, I explain about another method how to inverse the Laplace transform. And then today, our discussion is about the convolution integral, how to inverse Laplace transform using convolution integral. Okay, so first we have to consider that we have the following situation like this one. We have the input or xt here, and then we have a system here, and then we have the output yt. Xt is the input of the system, and then ht is the impulse response of the system, and yt is the output of the system. Okay, so we have a three item here, xt, ht, and yt here. Okay, in the time domain, in the convolution integral, we can write like this one. If we have the output yt is xt confold ht. Xt is the input, this is the input, and this is the impulse response, I mean this impulse response. Okay, so we use the convolution integral of phi from 0 to phi t, xt mean phi, h phi d phi, or this is similar to integral of phi equal to 0 to phi equal to t, h integral of h t minus phi x phi d phi. So this is similar. We can use the first one, or we can use the another one. The differences is we change from x to h here, and then h to phi to x here. This is similar. So in this case, xt and ht are said to be convolved, and the integral on the right, I mean that here is the convolution integral. Okay, so it can be shown like this one: Laplace of xt confold ht is equal to ys, the output in domain S. So it's similar to xs, hs. Okay, xs is the input in S domain, and hs is impulse response in this is the input but in domain S, and this is the impulse response also in domain S. Okay, so we can this is we see from this one. It's like we have the xt here. This is the input to the system, and we have the impulse response ht, and we have the output system yt, and then the impulse response is e power of minus 4t. So we can make similar illustration if we using in S domain like this one, xs, hs, and ys, but all in domain S. And then we also transfer from impulse response in domain T, like e power of minus 4t to 1 per s plus 4. This is the S domain of e power of minus 4t. Okay, so from the previous diagram, we know that xs, this one, is the Laplace of xt, Laplace of input system in domain T, and ys is Laplace of yt, the output in domain T, and hs is the Laplace of impulse response in time domain. Okay, so ht is called the system impulse response for the following reason. So we can use this one. ys, or output in domain S, is equal to xs hs. Xs is input to the system, and hs is the hs is the impulse response in domain S. Okay, so if we have the input xt in the unit impulse, like this one, so this is the impulse. So we transfer from unit impulse in domain T to unit impulse in domain S. This is the one. Okay. Since xt is an impulse, we say that yt is the impulse response. Okay. Okay. Okay, because of ys is xs dot hs. So if xs is 1 here, so ys is equal to hs, like here. So if xs is equal to 1, then ys is hs. So we infer the ys is equal to yt, so this is the impulse response. Or the inverse of hs is ht. So the ht is system impulse response. Okay, so if the xs is the unit step, unit impulse, so the ht is system impulse response and yt is impulse response. Okay, so it's very important to illustrate this picture that you have to remember that xs is the input, and we have the impulse response hs, and then we have the output system of ys. Okay, and then the impulse inverse Laplace transform hs is the system impulse response. Okay. For example, we have the xt unit step. This is the unit step ut here, and then we have the ht here, impulse response e power of minus 4t, and what is the output yt. So how to define yt? We can use the convolution integral like in this slide. Okay, so we can use this one. So we use that equation to define the yt, integral of minus unlimited to plus unlimited e power of minus 4 t minus phi u phi d phi is equal to integral from 0 to t e power of minus 4 t minus phi d phi. Okay, so it's equal to e power of minus 4t integral of 0 to t e power of 4 phi d phi. Okay, and then we got that yt is e power of minus 4t integral of 0 to t e power of 4 phi d phi, and then we make integral of this one. We got this one, e power of minus 4 t 1 per 4 e power of 4 phi phi from 0 to t, and then we got this equation 1 per 4 minus 1 per 4 e power of minus 4t ut. So this is the yt if we use the convolution integral. So we can use this convolution integral but in domain S to get the similar solution. So in the first one, you have to transform from the domain, time domain xt. This is the unit step. So the Laplace of ut is 1 per s. Okay, and then ht impulse response is e power of minus 4t. Okay, so ht become the transformation Laplace transform is 1 per s plus 4. So the ys here is xs dot hs. Okay, xs is 1 per s here, and then hs is 1 per s plus 4. Okay, so we can make aspiration a per s plus b per s plus 4. Using Heaviside, we got that a is 1 per 4 and b is minus 1 per 4. So it's become 1 per 4s minus 1 per 4 per s plus 4. So we infer from s domain to time domain. So this become yt is 1 per 4, 1 minus e power of minus 4t ut. So similar to this equation. Okay, so we can use this convolution integral using time domain, or we can use the Laplace transform. And I think in using the S domain is simple than using the time domain. Okay, so this is the practice problem. So for today, solve this practice problem. Is this from today assignment? Okay. Okay, what A, B, and C. Okay, and then we can use this Laplace transform to solve the circuits like this one. We have the input DC 12 volt, and then we have this circuit switch when t is equal to 0. So this is like switch on like this one. So the battery didn't connect after the t larger than 0. And then we have resistor here, and then capacitor here, and then resistor here, 3 kilo ohm. And use Laplace transform to find Vt for t larger than 0. And then we see from the circuit when larger than 0, so we have to use the voltage divider here. Okay, voltage divider, because when t larger than 0, so switch on like this one, so the battery didn't connect to the circuit. So we have to see using the voltage divider to find the voltage when when t is equal to 0. So we have using the voltage divider. You see that this one parallel with this one, and then parallel to this one. Okay, so we can determine the voltage using voltage divider 3 per 6. Okay, is it 3, this one, 3 per 3 plus 6 dot 12. 12 is 12 volts. So we got that voltage when equal to 0 is 4 volts. And then after the switch on, the battery didn't connect, so the circuit like this one. So we can use the Kirchhoff like this one, RC dVct per dt plus Vct is equal to 0. And then we can use this one. We divide RC here to divide RC, and this divide RC. We got this equation. And then we put the constant, I mean that what is the R here is the parallel of 3 and 6, so we got that this is a 2, and then C is 100 microvolt. So we 1 per 2 kilo ohm dot 100 microvolt. This is the 1 per RC. So we got this is the 5. So this equation become this one. And then this is the equation in domain time domain. We transform in S domain. So this is the differential. So it's become S VCS minus 4 plus 5 VCS is equal to 0. Why 4? Because this one is S VCS minus V0, and V0 is 4 here. Okay. So this is become SVCS minus 4 plus 5 VCS is equal to 0. So VCS is 4 per S plus 5. So this one we infer, so we got that VCT is 4 e power of minus 5t ut. Okay, so this is if you have the problem in circuit theory, you can use the Laplace transform like this one to find the solution. Okay, I think today is enough. We will meet in Wednesday to discuss the inverse Laplace transform application in the circuit theory. Okay, good afternoon. Assalamualaikum warahmatullahi wabarakatuh.